morning, ladies and gentlemen. Welcome back again to our class. Hybrid short course flood early warning system. Today is second day, and I hope you are well today. I didn't introduce myself yet yesterday. My name Ane Feriane. I am team leader of training cooperation. I will get the class activity, and I am very honored to be your moderator. I believe the session will not only broaden our knowledge, but also inspire further discussion and collaboration. We encourage you to engage activity during question and answer session that will follow after every lecture presentation. Our schedule today are 3 lessons. First, lesson from Mr. Christian Alphonsus Ligori from Delta Res will present the introduction and implementation to Delta Res FEWS technology. And second lesson from Mr. Rahmat Hamdani from Water Resource Department in Jakarta Provincial Government will present implementation of early warning system at downstream. And the third, the presentation from Dr. Andes Irfan Sudono and Ms. Radhika will present FEWS implementation in Indonesia. To kick off our session, I invite our first lecturer, Mr. Christian Alphonsus Liguri from Delta Res, who will present the introduction and implementation Delta Res FEWS technology. He is an expert and will sharing valuable insight to us. We are honored to have you share your experience and expertise with us. Will you please welcome Mr. Christian to deliver your presentation? Thank you.
Okay. Thank you very much for the introduction, Ibu. Hello, everyone. My name is Christian Alphonsus Ligori. I'm Indonesian, and I'm very honored to be here the second time already to share a little bit uh, about FEWS and the tools from the place that I work, Delta Res. Delta Res is a research institute in the Netherlands that works on water, on in inland and also in the coast. So we work a lot with water and also the surrounding areas. I myself is a practitioner that works a lot with hydrological modeling and also particularly here with Delta Res, FEWS, the tools itself. So today I'm very happy to share with you about the tools that I've used so far while working in Delta Res. Okay. I also want to share a little bit about the content of my presentation. So here I divide sorry, the screen. Yeah. So I divide my presentation into four sections. The first section is about uh, a brief introduction again on early warning system. I think yesterday Pak William already explained it very well on early warning system, but I want to review a bit and also to show how early warning system is very useful and also the forecasting itself. And of course, we will dive deeper on the structure of the tools itself. That's topic number one, the structure of the FEWS. Then after topic one, I will go deeper. I will talk more about the FEWS capabilities, what kind of features that these tools have and can be useful for us. And then what is the main concept of the FEWS itself, how it works basically. And of course, how we want to use this tool to visualize the data. Then I will also follow that with an example, like application in the region and also around the world, so that we better know how this tool is used around the world. And of course, I also will provide some links and also documentations that later can be very useful if you want to know more about FEWS. Maybe between the topic or the section, we can also have discussion like yesterday. If there is already a question, we will do it for after I share per topic. Okay, so let's start with a brief introduction to early warning system and forecasting. I think yesterday it's very good that Pavilion mentioned about early warning system, uh, about forecasting, the tools, the models. And I just want to quickly recap that early warning and forecasting is very common words that we hear these days. But normally, the way we provide warning is through measurement, by doing measurement in the field, and then we see whether there is a probability of a hazard to happen or a disaster to happen. Then we can provide a warning, and then from that warning we do something, we react to that warning. That's the traditional way to provide warning to the community. And where is forecasting in this diagram? So forecasting is actually between the measurement and warning. So this is another way to provide warning and to give warning by making use of more advanced tools like models, like weather forecasts, so that we can better be ready and also better prepared. I want to stress that early warning and forecasting are quite close, but also there is a difference between the two. Like in early warning, uh, I give the definition as simple as it's a way to let people know that something harmful might happen, so those affected can prepare and reduce the impact. It can be very simple as comparing the measured data to the predefined threshold. So it doesn't need to be very fancy, very sophisticated, very complex. We just need to have a measurement, and then we compare it with the level that we set in the field. That's a early warning. In the other hand, when we talk about forecasting, I often call it that it use more advanced methods or models. So the aim is to get more lead time, like more time to for us to be prepared and to make an action. That also would be very useful, allowing decision makers like the water managers to make better choices and coordinate with others to reduce the impact of a disaster. So although it's very close, but early warning system can be very simple. I would say that for countries or for region where we don't have a lot of things, maybe the first step is just to install gauges, refer gauges in the field that is connected to like a database, a server. That's already can be very useful if you have that in place. And the use of forecasts is very, I would say, very useful so that we translate data that we collect from the field into information. And then by using forecast or model, we can increase or get more time to be ready to react, to find a better solution with with the disaster itself. So it's very useful. It can support to us to make better decision, and of course, in the end, is to reduce the impact of such hazard. So that's a early warning system and forecasting. And then when we talk about flood early warning system, I think we should be very clear at the beginning what kind of flood event that we want, flood early warning system that we want to build or want to work on. Is it the flood from the rivers, like flooding coming from the river? Is it flood, flash flood because of high intensity of rainfall? Is it urban flooding because the local drainage doesn't have enough capacity to retain the water or flush the water? Or is it a coastal flood which comes from the sea itself? So before we make an flood early warning system, we should think about this first, which flood that we want to focus to tackle with, this, what kind of challenges that we want to tackle with. Because those floods might have different solutions. Like we have very sophisticated model, like in flood forecasting, like numerical weather prediction from weather forecast. We also have a model that translates rainfall to river flow, like rainfall runoff. And in some region also snow even. We also have hydrodynamic models. We have reservoir models, because of course in our river basin, we have reservoir as well, or structures. Then we also have flood inundation model, urban drainage model for urban flooding, and of course, coastal model to provide us the seawater level at the boundary, at the downstream boundary condition of our model. So we have so many models that probably we can use some of them, or maybe we can use all of them even if we need to address our challenge in flood. But we need to know first again what kind of flood that we are dealing with. Is it the coastal flood? Is it the riverine flood? Is it the pluvial flood or the compound flooding? Maybe we need some, but maybe we don't need all at the beginning. And again, it can be very simple, like we just install gauges and connect it into system, a database, visualize it in our computer, website, whatever, and we put certain threshold. That's the very basic one, I would say. It's still considered as flood early warning system because if the water pass that threshold, then we provide warning. But why we need this model? That because just now I said that the very simple one of flood early warning system is just installing gauges, river gauges, and put a threshold, defines a threshold, water level threshold, and if it passes that threshold, we give an alert or warning. So why we need this kind of model? This question can be answered in this slide. That again, if you only have river gauge, you only monitor, and then if the water level pass certain threshold, then the threat is recognized. Then you start to react. That's the only moment when you start reacting. You only react when there is an information that the water level already quite high. And then from that threat recognized, you will do notification telling other communities to react. Then you maybe also make a decision. You produce a mass warning to the community. Then the community will take action. And then if you see here, from threat recognized to flood occurs, that's the time that we call lead time, or the period where you have to react or to make action. This is the traditional way of providing early warning system. Then we can compare it with if you have a forecast or a model. Still, you also still need measurement in the field, but then you use that measurement and put it into the model together with like weather forecast. You can produce the water level in the near future. So you will in the end get additional lead time because you know the threat much earlier than if you don't have such forecasting system. Although here maybe the schematization doesn't show a very big lead time difference, additional lead time, but in reality, this lead time can increase to like many days, 2 days, 3 days. So we know if there is a flood in the coming 2 or 3 days with the help of model and also forecast. So this is why forecast and model can be very useful to increase lead time, to give us more time to think what kind of solutions are available, what kind of warning that we should provide to the community. And of course, if we can make it much earlier, people can make action better and also can reduce their loss or their risk. Then in more detail, here I have a schematization that shows the measurement, hydrological and meteorological observation. We have model, you name it, many model there are. Then we also have meteorological forecast from meteorological agency that we can use and put together into our model. So we combine observation. So you may have this kind of graph if you combine those three components: the observation, models, and forecasts. Like here you have, in blue you have the precipitation. In red you have the rainfall forecast. Then you also maybe have water level measurement and also the discharge. So all are available, hopefully. But if not, you can also still use model. So maybe you only have rainfall. You don't have water level and discharge measurement. So we use model to translate rainfall into water level. So even though you may not have water level, the historical water level, you can generate that, you can obtain that from a model by putting the rainfall. Then from those model, after you run the model, say for a certain period until this red line, you can then also provide the model with additional data, which is the rainfall forecast. And then you get the rough estimate of how the water level and also the discharge in the coming periods, maybe days, maybe hours, depending on how long the forecast gives the prediction or gives the projection into the future. So this is the process of the forecast. We of course need observation still. That's why I think still, if you don't have a model yet, you can start investing uh, on installing river gauges, rain gauges, and start thinking the threshold or defining the water level threshold so that you can still provide warning. Then I think I already say a lot about warning and what is warning actually, and what is the use of warning and how to respond with that kind of warning. This is what I want to share a bit about warning. So warning is not actually not the end. Warning needs to be followed with something. Say you take action, you tell people so people can react. So it's not really the end, but it's the beginning of the process. Then for us, like professionals, when there is a warning, like here in this graph, you can see that this is the discharge. If it's passing, if it passes a threshold, then professionals like water managers, water operators, flood early warning operators, they need to follow certain procedures, like standard operation procedures. But if you think the other way around, if there is a warning to the public, what kind of information that we should provide? Do we need to tell, like they need to read this graph? Maybe some of the people can read or understand what this graph means. But for the public, I think it's much more useful if they are given the information, what kind of thing that they need to do or how they need to react. So warning can be seem to be a simple word, but in reality, uh, warning can be interpreted differently for professional and also for publics. For professionals, yeah, you can provide this graph, and they can understand. But for public, maybe we need to provide more detailed information, like, oh, you need to react this. This is gonna be this. The flood gonna be this destructive, gonna be causing, gonna be this height, gonna extend to which area and for how long. Maybe that would be very much useful for them. And of course, there are different colors as well that is used in warning: red, orange, yellow, green, to give the different level of threat of warning. So so in this slide, I want to uh, uh, ask everyone to start thinking. Let's say if we want to build a flood early warning system, the first thing that we need to do is to set up our goals. What is this flood early warning system for? Is it is it going to be providing warning based on only rainfall data or water level data or discharge data, flood depth, flood extent, or even flow velocity? Because sometimes in some region, the river flow is very fast and can be also very dangerous already. So we need to define first what kind of parameters that we will use to give warning. Then, after you define the parameters that you want to use, we also need to uh, think: Are we going to focus on a point, a single point, or an area like the flood extent? And for which time period? Is it uh, is only looking at the past, like using the river gauges or the measurement, or also looking ahead by using a forecast? Maybe how long? 2 days, 3 days, uh, 5 days. So I want to ask everyone later, if in your organization you want to build a flood early warning system, please start from this. From what parameters, which area that you want to focus on, and how long the 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 time period that you want to focus on. Only the past or also to the future. Then after you also already define the goal, then start thinking about the data that is available or the tools that you might already have. Let's say maybe you already have monitoring, like the rain gauges, water level gauges, or even radar sometimes with the help of meteorological agency. Start looking again on your existing uh, instrument or tools. Then also after that, you can also start checking, listing all the models or all the tools that you have. maybe the model that was developed for building a dike in your area can be used again for flood forecasting. So list those models. Maybe a simple model can already be useful, hydrologic model, hydrodynamic model even. But again, it's optional because, of course, you can use model to give more lead time, but the complexity also gonna be increased. And I also want to think together with you in terms of process. Say that you want to develop a flood early warning, but you don't want to use any model. What is the step? What is the step that you need to do in terms of providing warning? Well, here I provide some. Like first, you need to collect the data, of course, from those devices that you have. So data acquisition is very important. And then you also need to validate, of course, the data, right? Otherwise, maybe it gives a very wrong value. Maybe you need to remove negative value, which is nonsense, or maybe, yeah, maybe for some area, the water level can be minus. But you need to check first whether the data that you get from the field or from the device is already correct. So you need to do data validation and inspection. Then if you have already the threshold, you can then use that threshold or define the threshold to provide warning. Then again, the warning can be very different for professionals and also to the public. To professionals, the graph that I showed earlier can be already good enough, but for the public, I think we can provide more description. Like, okay, this is the flood. The flood is very harmful. Can be like how many meters, and for how long? Because that would be very much easier rather than looking at the graph. Model or tools. The first step, of course, still the same, like data acquisition. Maybe this time you need to have weather forecasts from the meteorological agency. It's still the same. The second part is to do validation. Again, still, of course, data validation is very important. Then, because you will use a tool or a model, you might need to change the format of the data. Maybe the format is not doesn't match yet with your model, so you need to convert it or do pre-processing so that it can match with the model input format. Once the data is already the data format is already matched, then you can start asking the model to run, to do simulation, even doing scenarios if you want. So manipulating the input. And then once the model is run, of course, we get the result. And then the result can be in graphs, in tables. And then in a flood early warning system, there is an option as well to do uh, to choose whether the forecast generated is approved or not. Because maybe we want to modify the model input or we want to make changes with the model result before we publish it to the community. So this approving a forecast can be useful before making the forecast to the public. And then last, of course, the same. We provide the warning and disseminate to via website, via WhatsApp, via many social media that we can think of. So here we already see that the process, if we use a model and without model can already be quite different. And of course, if we use model, we need more process to make the early warning system works. So that's about the early warning system and flood forecasting. And now I want to start talking about FEWS, FEWS tools. And I want to tell a bit about what kind of topic that I will discuss in this event. Because FEWS, we have so many courses here. We have basic, we have more advanced, like spatial water information system, WIS. It's like for storing data, like a database. We can also use for water quality purposes. We can also do fluvial modeling, like doing a hydrodynamic model. We can also do it for coastal, and also even on the other side, ICT training. We also have a course for supporting the IT people to connect or to build the FEWS system in operational setting. So I want to tell which part that we are going to do today. So we are going to talk about only the basic today. And of course, we also have an event that you can also follow remotely later on. And we always do it every year as part of Delta Rest Software Days in the Netherlands. So these days after COVID, we also have a hybrid. So I really encourage you to also join and follow the online session as well. So why I only say that it's partly today that I will talk about the basic course only part, because I think within 3 hours we will not have enough time to go deeper on the configuration, on the technical aspect, like how to set up this, set up that. But I will talk about the concept and how this model can work and use around the world. So I will talk the basic course of FEWS and only some part of it. Later in the last section, I will also provide the links to join the other course as well. And here is the FEWS itself. I hope everyone doesn't already think that this is a model. I hope not, because this is actually just a platform to integrate things, to integrate data, to integrate model, to integrate a script even, let's say Python script, programming languages. And we use this platform to also disseminate the warning to the community. So this is like an adapter for many things, for data, for model, for numerical model, for weather forecast, for radar, whatever you name it. most of the time we can connect with this platform and nicely visualize it in one window or one screen. Of course, the name itself, FEWS, stands for Delft Flood Early Warning System. Delft is the name of the city where our main office is located. So it's in the Netherlands, and that's why we have Delft at the front. And yeah, the software brings the forecast, all the forecasts that I previously mentioned together. And this platform is also considered as an open data management and modeling tool, which means that everyone can see the data together, the same data, and also can connect any model that you want. It can also be very specific for an individual or organization because it's very modular, built on existing and investment as well. So we don't build from scratch. Previously, we have a tool as well, similar like FEWS, that was also developed by Deltares called HIMOS. And we use that concept into FEWS. And then this is also can be run in Windows, Linux, Mac. So many operating system, and can also be very scalable. Once you want to have it in the cloud, you can also have it in the cloud. Or maybe you want to extend the model or have a bigger model or complex model, we can also accommodate that. And sometimes people think this is an open source platform, which is not. This is an open, free to use software. I always say free to use software, not an open source, because you cannot really see the code behind. You can use it for free, but you cannot change the code behind. And then it is also has a lot of features. So in one interface, you can have data import and management, and it can also be automatized. We can also do the data quality check that I also previously mentioned and also important. We also can ask the model to run, to execute the model. We can visualize the data in the same interface, and then even analyze and compare the different runs or simulation. And last but not least, we can also produce reports that can be a bulletin, a warning report that can be shared to the public. And then, so this is in principle, we all now already know that we have this data. Say we have weather forecast, we have telemetry, field measurement. Then where is FEWS? FEWS is just below it. So we import those data using import module. And we have a database to store all the data that you want to import. Then inside the FEWS, we have also a processing and validation module. So in this module, FEWS will check the data that you just import, whether the data is giving reliable value or not. Maybe you get a sudden jump. Maybe the water level is normally 2 meters and suddenly spike to 4 meters. And it can give you a warning about those spike. Or even, or maybe in another example, you have water level 2 meter, and then suddenly -1 or -3. So this kind of check can be done with DelFuse. Once you already process, validate everything, we can use a module called general adapter to connect with the model that you have. Maybe it's a Python script, maybe it's a a simple rainfall runoff model, and then you prepare the data that is already imported into the database so that it can match with the format of model that you use. So this general adapter is really just making sure the data can be used by the model, and the output of the model also can be imported back to DelFuse with certain format that DelFuse can understand. And then another module that is also often used is the export module. Or we although there is a specific export module, but the 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 term that I use here is export. So we can distribute the interface or the platform to many people, because the database can also be stored in a server, like client server system. So people will see the same data, the same interface, and even can be shared to the emergency responder, to internet, and even to archive. Because in operational context, uh, I I noticed that we have a lot of data already, like radar data, weather forecasts. And if we only put everything in the database will be full very quickly, so that it also slow down the application. So that's why we need another archive, another database to store the historical simulation or historical data that we might not need to use in operational context. So these are the very simple what is it? Framework of DelFuse. We have import, we have processing, export, and general adapter. In principle, DelFuse is built for hydrologists so that they can make use of the platform to provide warning and also show the flow discharge at a certain area. There are three installation options. Here we have standalone, client server local, client server in the cloud. In simple term, standalone basically is just you install the DelFuse application in your computer. And once you install it, if you do modification and your friend compute, and in your friend computer they don't do any modification, then you will not see the modification that you have in your colleague's computer. So it's really the database stored in your computer. Whereas the client server local, here you put the database into a server, a really physical server. Maybe in this building, there is a room to store the server. And then from that server, you put all the data that you have collected, radar, weather forecasts, rain gauges, rainfall, water level. And then with operator client, DelFuse operator client, you can access to the database. So the same, you do installation in your computer, but this time everyone who installed the operator client will see the same data instead of in standalone. If you do some changes or import more data, all will be stored in your computer. But if in the client server local, you all will see the same data set, which can be very useful because sometimes in the let's say in Indonesia at public works, we also have many departments uh, are in different island as well, and we might need to know the status of the river itself. And with this application, the client server system, everyone from the central and also the provincial and even the city government can see the same data set. Of course, here we have still the physical server, like so that's why we call it client server local. But these days, we also have technology that allows us to put the server in the cloud. So we don't have any physical server anymore. Everything now is in the cloud. But in principle, it works the same as what you see in this right diagram, the client server. Everyone will still see the same. The only difference is that you put the database in the cloud, like Azure, Microsoft Azure, AWS, and Docker. So you have three options, but in reality, in reality, uh, in order for you to have the client server local or the running operational system, which is in the client server, normally you build your system first in the standalone. So you do testing, you do configuration, you do changes in your computer. And once you think, oh, the workflow is okay, it's good, everything is working well, then you start uh, uploading into the server. And then everyone will see the workflow, you see the data, the same data set, the same interface. We also have another nice components that often used as well around the world, which is the web service, the REST web service and APIs. Basically, these two are a way to allow, let's say, programmer to build a nice website from our collected data set. From the database that we have, we already import a lot, right? And from those database, we give an option for people to access the data and display it whatever they want. Maybe to their phone, mobile phones, Android app, maybe to a website, maybe to their own system. So we have those components that allows people to connect and collaborate with. And also the archive solution that I mentioned earlier, that we cannot store everything in the database. It will slow down our system. And in principle, the component of FEWS consists of two. The first one is software binaries, like the code itself, which I said it's not open source. We cannot see really the code. And also the instructions, the XML, the configuration, CSV configuration. Maybe some of you never heard about XML, but I hope for CSV, I think it's still familiar, like it's an Excel format, but a comma separated format, like a tabular one, but it's much simpler. So we use this to configure our system, the XML and CSV. And so the binaries normally are we don't do anything with the binaries. Delta Res developers do some update on the binaries, but us, FEWS users, we only focus on the other side, or the hydrologists, we focus on the configuration directory, which is here. So we have a folder called config, and inside this, you can do changes. So what is XML? Because we will, in a basic course, in a normal Delta Res basic course, we will focus on this XML, how to modify, how to make changes, how to update the system by changing this XML. So XML is just a format, a configuration files that we use, and it stands for extensible markup language, and it written in simple plain text, so you can really see what is inside. And this XML is not like regular text file in Notepad text file, but we use another criteria, like a format, a file called XSD, to validate the XML. So we cannot write whatever we want in the XML. We need to adhere to certain criteria that is already defined in XSD. And here is an example of what inside the XML. We have a location ID called Basak Choktomuk. And then we have also the coordinate. This is just an example of how we define a location in the FEWS configuration. And then what is XSD? So XSD again is just a way to validate our XML file, to make sure that we don't write, or the user doesn't write whatever they want to the XML. Like this gives a structure to write the system, like building blocks of an XML documents. It also defines the order in which this element can be included. So also like the position is also ruled by this XSD. And then XML is valid when organized or according to the open schema XSD. So every time you run the FEWS application, it will check first whether all the XML that we have changed is valid. And it's the XSD file is also available in the bin file. The XML file itself can be opened using normal text editor like Notepad and Notepad++, but we suggest that we use a specific XML editor so that it can check the XML file that we make. There are several XML editors which can validate the XML file. The first one is XML Spy, and the second one is Simple. Both of them are free, and it can be used. For us, let's say the FEWS configurators, we use this a lot to check the XML file. Yeah, in normal course, normally people will be asked to install, make some modification, but in this course we will not do that. But in principle, you need a kind of tool, a software that do the check of the XML file. So to summarize the first section, so I hope that we all now agree that in order to make a flood early warning system, we need to have a clear goal, what kind of system that we are developing. Because the main goal for early warning system is that we need to provide information or warning that can be accessible by the end user. That's the main goal of early warning system. And flood early warning system can be very simple, right? As simple as one that triggers warning when rainfall or water level exceed certain threshold. Despite of the uncertainty of a forecast, the use of forecast in early warning can also be very helpful, as it will increase the lead time, allowing decision makers to make better choices and coordinate with others to reduce the impact of a disaster. Yeah, now we all, I hope that we know what is lead time, and we can add additional lead time by using forecast. Then we also know that FEWS is free to use and can bring various types of data and models together and visualize them in single application. FEWS also is not a model itself. FEWS is just a platform to connect data, model, and also help us to visualize data and disseminate warning easier in one platform. The quality of the forecast, of course, depends on the model that we use, right? So we can have many models if we want, but you need to validate and make sure that the model also correct before we put into an operational flood early warning system. And the FEWS is made of XML configuration file. And maybe I haven't mentioned this, but actually XML file is not really a programming language. I would say it's more like filling a template. So there is a template of XML file. You just need to fill values or make changes inside the XML file. So once you know the template or use that template a lot, you will know you can use that template again for another application or another workflow, like import module. You can use that import module for, let's say, import water level data, but you can also use that for rainfall data, radar data, which is gridded data, like cell by cell. So it's really, I would say, not computer programming, but more like filling XML template. Working with XML, XML editor is recommended because we can then validate the XML file. And we have also 3 flavors of installation of FEWS: the standalone, the client server local, and also client server in the cloud. Well, that's the first section. I think we can, I think it's better that we have a discussion now. Like if there is any question in the chat or in the room, I think we can have like 3 or 4 questions before we move on to the next session. Yeah.
Well, thank you very much. Good morning, Mr. Christian. And on this opportunity, I am really interested with your presentation just now. That now you just mentioned that the forecasting is divided into 3 categories. The first one is measurements, warning and response, if I'm not mistaken, sir. And my question is on the first subsection, which is measurement. What kind of measurement is it? Is it the monitoring, like you just mentioned, that rain data, radar, or water gauge? Because you just mentioned that Delta Race Group is a research group which is originally based in the Netherlands, if I'm not mistaken. And I was just wondering if there are any standard operating procedure for this forecasting type, because for your information, I was just about to begin this kind of forecasting method. So your insight might be really helpful for me. Thank you very much, sir.
While waiting, maybe I can try to answer. So please correct me if I'm wrong. Like you are asking about whether there is an SOP, like, and in terms of measurement, what kind of data that is that it's referring to. Yes. Okay. Yeah, it's true that, of course, in the Netherlands, they have their own SOP. Although, to be honest, I myself have never seen it myself. Maybe because it's in Dutch that they don't have it in English. That's why also whenever, let's say, I was in the Netherlands, I tried to ask. They cannot really give like the SOP, but I really believe that they really have an SOP, but in the Dutch language. In terms of the measurement, true, like the first thing that I think we recommend to have is at least for flood early warning system, that must be the water level gauges. Yeah, that's the measurement that we need to have, and hopefully it's already a telemetry water level gauges that can send data to database. Whatever database that you choose, let's say Postgres, SQL. This is a bit more technical, but it's basically a database. You can choose whatever, and FEWS can also still connect to the database and get the data. So in terms of measurement, through water level gauges, rain gauges if you have, or maybe you can collaborate with Meteorological Agency as well, or BPSDM in Indonesia. And then radar data, if it's possible. Why radar data? Because the way that I also see in the field in the flood early warning system is that if you have only rain gauges like point locations, sometimes the distribution of the rain gauges are not so nice, the distribution, like it's very far from another. And if you make interpolation between the stations, it's maybe not very accurate, I would say. So, and also sometimes the rain gauges doesn't capture the rainfall correctly, or maybe missing data doesn't work. So with radar, you can feel the missing with the radar data. So later on, I will also show that FEWS can do merging between and filling if there is any missing data. So rainfall data is very important. Radar, if possible. Weather gauges, water level gauges. And these days, I think we have a good opportunity to access to global weather data. So satellite imagery, GPM. This is some of the remote sensing products, GPM, ERA 5, that can already be used if you don't have any data at all. So those kind of data set can be think of when you start building a flood early warning system. I hope that's answer your question. another question.
Excuse me, Mr. Christian. My name is Boy from Technical Implementation Unit for Hydrology and Water Environment. So Delphius is a platform that visualizes data and model output rather than being a hydrological model itself. And my question is, can Delphius facilitate the integration of different Delphius standalone? For instance, if each unit develop a standalone views for their respective basins, can this be merged into a single national scale model, or the integration visible only by inputting the hydrological model into a specific views that we wish to combine? Thank you.
Thank you, Mr. Boy, for your question. Sorry, I missed the last part of the question. Can you repeat the last one?
Can we merge the standalone views from each unit into a single national scale model, or the integration only by inputting the hydrological model into one views?
Thank you for the question. In principle, to answer your question, yes, the standalone can be, yeah, we have maybe developed several systems, let's say for Bandung, city in Bandung, then for Jakarta, Semarang city, you can still integrate it into one platform. Or yeah, but then you need to, let's say, like do copy paste the XML configuration and making sure that the XML doesn't have the same name, and yeah, otherwise you will get conflict. That's the first option. The second option, if all the system, let's say, already operational, yeah, and standalone, normally it's still in your computer, you run it manually. But if it's later on, all the data is stored in the operationals in the server and it's run every day automatically, you can just take, let's say, I think the important thing from merging is to get the output, right? Output of the simulation. We can use or take the output only from the database, pull it into one application, Delphius, if you want. That's another option. But of course, if the operational client, those operational client for let's say Bandung doesn't work, then you will not be able to get the data from it. But yeah, in the other hand, if everything in one system, and if everything doesn't work and like the server goes down, then you don't get any data at all. So there is an advantage and also disadvantage of like choosing the two options. But yeah, in general, you can put it into one application, one big platform. Something that to be considered is only the capacity of the computer, and also the RAM of the computer, the memory of the computer, and the storage of the computer, like the hardware part of the computer that we can think of. Yeah, thank you. I hope that answers your question. Do you want more? Maybe in the chat. Okay. If there is no more question, then I will try to move on to the second topic. So I hope this part will be more exciting, because we will really see what kind of features that Delphius have, not only, let's say, the XML file that we don't do any changes, but here I will talk deeper about what Delphius can do, the main concept, and how we visualize the data. In the previous diagram, maybe we know already that there are several modules like import module, then pre-processing module, general adapter module, and also export module. And in short, everything is in this diagram, like in a very simple way. Like import data, it can be from files, it can be from website, it can also be from FTP, like a file transfer protocol. And then for general adapter, we have several. Here we have internal model, I mean Deltares own model, and also external model like Mike 11. But in principle, the general adapter is used to connect with the model that we have. Then we also have export module to export the graph, the table that we already put into the database, and maybe even make a bulletin for giving a warning to the region or to the community. So basically, Delphius provides generic functionality that we call modules, which can be easily configured and organized for specific application. Here, modules also mean modular means that it doesn't need us to use all. We can just use some part of it that we think can be useful for our system. Normally, in a system, we always use import to get the data into the system. We do some transformation, processing, pre-processing. We use transformation module. Then maybe if we have a model, we use general adapter module. And in an operational context, you may need to use export module, but in a standalone, or if you only want to visualize everything in your system, I think these three is already enough, like the import, the transformation to make changes, modify the data, and also the general adapter to connect with the model. And here, the generic workflow that I'm talking about. So Delphius, if you want to configure a Delphius, we always talk about configuring a workflow, like step-by-step process in order to provide warning. So we do import, we do processing using transformation module. We use general adapter to prepare the data. There is a pre-adapter. We ask the model to run, and post-adapter to make sure that the output of the model match with the Delphius import format that Delphius can understand. Maybe from the model output, we still want to process, to change, modify the output. We do transformation again. Then we visualize it and export into other format, maybe CSV file, maybe PDF file, maybe HTTP file for website. So this is the generic workflow that we always use. When we talk about the adapter, many because Delphius has been there for a long time. It is known that many model providers made their own model adapter for Delphius PI interface. So Delphius PI is a format that allows model to connect or to give the output to FEWS. But that's in the past. These days, we have a nice format, many options as well, like NetCDF and other supported format like raster file, TIFF file, like gridded cells. That can also be used or can be imported into FEWS. So we don't, yeah, although in the past we use FEWS PI, but these days we also get the choice to also use another format. And some models that already be able to connect to DelFuse are a lot, like SOBEC for hydraulic modeling, like flood modeling, Ribasim for water distribution. Del3DFM is the successor of SOBEC, so it's also hydrodynamic model. But sometimes when model developers build their adapter and put into, let's say, our documentation. So we have a Deltares DelFuse public wiki where all the documentation of DelFuse are there. And there is also a challenge that if model developers develop the connector, sometimes they maintain it, sometimes they not. And when other people look at the website and want to use that connector, sometimes it works, sometimes it's not. But we are very sure for our model, because we also maintain it ourselves, the connector will always be fine. But for external model, sometimes the user need to check because the adapter itself was made by the model developers or maybe in collaboration with Deltares. So those are the challenge when we use external models. But still, we have many options, many models that we can integrate with DelFuse, like WFlow for hydrological model, SOBEC for flood routing analysis, and so on and so on. You can have a look all the list of the models that we are already have an adapter, a direct specific adapter in the link that I provided there. Talking about the main concept of FEWS. So yeah, just now we know already the workflow, like there is an import, there is a process, run model, post-process, export, archive, reporting. But then DelFuse itself is built based on these three main components or main things. The first one is the workflow, which is what you see in the diagram. Yeah, the import, preprocess, run, post-process. That's what we call a workflow. So a series of steps. And then inside, there is a module. So import is import module. Preprocess is preprocess module, like transformation module. So it's a module that is used per step. That's we call module instance. And in order to make sure that each module is connected one to another, we use time series. So here, the time series is like the bridge of the modules, which connect the data flow between the module instances. And of course, without time series, yeah, the workflow will not work because everything is connected with the time series. You work a lot with data here, and DelFuse is built around data. Then here, I want to share with you what Delphius is capable of. So here I have an example. Maybe not, maybe before that. So Delphius can support various data format. As I said, CSV file, NC is netcdf file, GRIP is for raster file that often used for weather forecasts, ASCII file, HDF4 file. This kind of files are supported, so we don't need to worry anymore with a strange file that come from meteorological agency. We already cover most of the meteorological format. And what is nice about Delphius is that normally in another platform, or if you want to build from scratch, you only think about importing data and making use of the data. But in reality, we have a lot of strange values or odd values or missing values that is also in the data that we get from the client, from our meteorological agency or our device. So Delphius has capabilities to give a flag whether the data is unreliable or can be considered unreliable. And it with a simple configuration, we can have this kind of figures where you will get a highlight in the table and also below the graph somewhere here that shows that there is a unreliable values or very strange values, both mixed, both the minimum, the soft minimum, and also the hard minimum, and also the hard maximum. So we put a threshold, say for water level. If we get minus 100 or below, even below 0, it's already not correct. So we put hard min to 0. Whereas for the hard max, maybe for particular area, we set that into 10 meter. It's already quite high. That's the maximum. Then we can set that threshold for hard max to 0 to 10 meter. So basically, Delphius is capable of doing that, quick data validation that can also be displayed both in the table and graphs. Then we also have a lot of transformation. We can do like simple mathematics, like if you have a formula that requires multiplication, addition, subtractions, we can use user simple transformation. We can also do the same for raster data or spatial data. We use spatial transformation. And sometimes maybe you have a raster file that is bigger than your catchment or area of study that you want to clip the data. We can also do the clip using spatial interpolation. And then we have a merge later in the next slide. I will show how useful merge transformation is. And then aggregation, maybe you want to aggregate the hourly rainfall to daily rainfall. We can use this transformation. And of course, the adapters that I shared earlier with all the software that is capable to be connected. And here is the nice example of the transformation that is used a lot as well in many operational system, flood early warning system. So here, let's say we have observation data in green. Maybe this is for for rainfall, because we use radar. So we have rain gauges, observe rain gauges, but we have missing period at the beginning and also somewhere in the middle. And then but at the same time, we also have radar data, which is here on the top. Also, maybe radar data sometimes works, sometimes not. I don't know, depends. But in this case, let's say there is a missing data as well. So we can fill this missing data by with the level of importance, by giving the level of importance of the data that we have. So here we will use radar data if there is. So here the importance or the prioritization is from radar data. So if we have radar data, we will use it. If we don't have radar data, we will use observation data. And if we don't have both, we will use default value that we set. Maybe 0 should be good, because sometimes some model cannot be run, otherwise you provide any data. So you need to fill 0 still to make sure that all the data for running the model is available. So this is one example of how merge transformation can be used. Then we know already the Delphi's capabilities. Now I want to talk a bit about the time series set. So earlier I mentioned that time series set is used to connect one module to another. And here on the right, you can see how the time series set looks like. So it contains several elements here, like module instance ID, value type, parameter, location, and so on. But in essence, this is used to make a unique ID for your data. This is used to make a difference from one data to another, like the parameter, like what the time series represent. Is it POPS? POPS means rainfall observation. Sometimes you have HOPS, like water level observation. Of course, you can define it your own, like the rainfall observation, maybe ROPS, R.ops. But this is mainly what we use, POPS. And then location, of course, is it a raster data or a scalar data, like a point location or an extent of your data? Here the location ID is imerc underscore world. So here we use, we give a name of our grid file called imerc underscore world. So that's location. And then time step, of course, the time step of the data itself can be minutes, can be hour, can be decadal time step every 10 days. Many options. And then time series type. This time series types actually defines its behavior in the system. Like if it's here we have external historical, meaning all the historical data that that this time series is talking about, or we are defining this data as a historical data. There is also external forecast that is actually data, forecast data that we want to define in our time series set. There are more actually, like simulated historical, simulated forecasts. But in principle, if you have data not from a model, you always define it as external and choose whether historical and forecast, as in depending on the period that you have. If it's historical, then external historical, but forecast, then you define it external forecast. Once you do simulation using this external historical, then you can give a name simulated historical for past simulation, and for future simulation or prediction for simulated forecast. Then we also have value type, which defines the data format. Here we have grid, so it is a gridded data. We can also have a scalar data for point location. And then the last one is module instance, which is also quite important. So we know already module, that module is like the component of a workflow: import module, transformation module, process module. But here module instance ID is just a name that you give for the, let's say here, import module, because I believe this is for importing GPM data. So I give a module name, import underscore GPM server. So this is just a name, but this can be also used to distinguish one module, one time series set to another, because maybe you also do, say, transformation. Once you import data, you clip only for a smaller area, and then you use transformation module, and you give module instant name transformation GPM. By changing the name, and you already have two different time series set. And if you call the transformation GPM server, the one that you will get is the clip GPM. But if you want to get the full extent of your data, you should select this first time series set instead of the module in the time series set with module instant ID transform GPM. So basically, these are the elements of DelFuse that that is very useful and used a lot for the configuration. Here is another example, like I'm using a transformation module, and on the top we have I have a variable called P manual day field. It's just a rainfall day, a daily rainfall data. But then I want to aggregate it to monthly rainfall. So I use transformation module with element aggregation, accumulative, with input variable called the P manual day field with this time series set in the previous slide. And then the output is another time series set with transform. Let's say I give a name, transform WMO SMDB module instance, just a name with this time series set. By configuring transformation like on the bottom left, this can already be used. Like Delphius will understand that, okay, I will do aggregation for this time series set with daily time step into the output with 1 month time step. And we're only specifying something like this. This is this very simple example. Delphius can understand and do some processing inside. The same you can do it for other, yeah, say like when you run a model, you can also do a similar step like this. Then in terms of visualization, Delphius has a lot of options. Like this one that we call map viewer. So in this window, you can easily see your stations, where are the stations are located, and also can be used to tell which area is now experiencing flooding or under alert condition or warning condition. Because maybe in this projector you cannot see well, but there is an icon there which can be changed depending on the flood condition. If it's under warning condition, then the icon can be changed to yellow color. If it's orange, if it's alert, then it can become orange. And if it's danger level, then it can change to red, which can be very useful. Another option to visualize data is by showing it in a table and also in a graph. So in your screen, in the screen, you can see that we have, I think this is the water level, and also these charts. I'm not entirely sure, but in essence, you can plot several parameters in one graph. So you can do display groups together. And you can also quickly export the table and graph into CSV file or PNG file just by right-clicking from the image and save as the files that the file format that you want, which is used a lot. Then we also have for spatial data, for raster data, we also have a spatial display. Normally is used for displaying raster data or gridded data. Like for earlier I said remote sensing data, like GPM, global precipitation measure products, they can provide rainfall data. So this is one of the example. We can visualize their product. We can import and visualize it. We can also have radar data here. We can also have forecast data displayed in this spatial display. Apart from these three, we can also do a very specific display that we built ourselves. It's called schematic status display, because sometimes it might be very much easier for the operators to see the schematization instead of looking one by one the location. If with this schematic status display, you can build your diagram yourself and still connected to the table and also the graph. So let's say if I click on this yellow rectangle that tells a location, it will gives me the table and the graph on the data display. So there are many options that DelFuse can do. And later, the next session, I will also share a bit more about how other countries visualize and make use of this visualization. And to summarize for this section, I hope we all know that now DelFuse has a lot of built-in capabilities, and it's the key advantage of using DelFuse as the core for early warning system, because yeah, many features or many process that we see at the beginning, the forecast, and can be done with one platform, DelFuse, because it's very flexible. It can connect with model, can connect with different data set, different formats, can be used also to distribute the data so everyone can see the same data set. If we put the database in the server, so there are many things that can support the forecast and also disseminating warning to the bigger groups. And then second is that DelFuse is a modular toolbox of which can be customized per user needs. So yeah, DelFuse basically again comprise of several modules that doesn't need to be used all, but only for specific use cases. If you only want to visualize, then maybe import the data is already enough. And also for database, water information system. So I had the chance last year to build a water information system in Cambodia. And in the beginning, we only do integration from several systems. We don't have any model, but we do integrate all the systems that they have, from radar, from water information system given by the France, from another donator like UNDP, ADB. So there are several systems with their own database, but then they don't, at the moment, at the time, they don't have one application where they can see all the stations that they have national scale. So with DelFuse, we can do integration with different platforms, although it's maybe already outdated. As long as we can have access to the database, we can still pull the data. And also already the good case of this is that we make a backup of their old system as well. And now they can see in one platform all the meteorological stations that they have, which are still working, which are not working anymore, which are giving reliable values. So everything now is in one platform. That's the nice thing of DelFuse. And last time the implementation was done in the cloud. So I was very fortunate that I was able to do that together with the team to build those systems in the cloud. and that works. And then the third point for this session is that whenever you create or setting up a workflows, you will also get a better clarity on how the flood forecasting works. With workflows, you have a logical thinking process that you can also share to other people, that this is how we do it. We do import, we do processing, we do model run, export, etc. And this is open to everyone. So everyone can learn as well, can see that, oh, this platform use this kind of workflow, they set up this workflow, and people can learn from it. The main concept of FEWS, we know workflows, the logical sequence of module instance. We have also the module itself, import module that is used to handle the data. And then the time series set, which is used to connect data flow between the module instances and also to distinguish one data to another. And there are several ways to visualize your data. The one that within FEWS application via map viewer, data display, table and plots, special display, and of course the most advanced one, or the but also can be very useful, is the schematic status display. So that's covering section 2. Maybe to make the session more live, I also again open discussion and also question in the room and also in the Zoom, if there are any. Maybe 3 to 4 questions before we move to the next topic. If there is no question, that's also fine. We can move to the next section. Maybe this one is more interesting as well, because we will see the implementation of FEWS around the world. Maybe it can give more insight and also later on question, hopefully. It can be you feel free to ask any question. Maybe in your workplace, you need to develop a system, but you don't know how to integrate it. It can be very technical. That's also fine. It can be very conceptual, also fine. Any question, please feel free to ask. Okay, then I'll move on to the last topic, which is the FEWS application in the region and around the world. So given its flexibility and modularity, FEWS actually is used a lot for many applications. We have drought forecasting, flood forecasting, reservoir management, hydropower, water information system that I have in Cambodia, navigation purposes, water quality. Earlier, there is a specific course to configure water quality in FEWS, and also even for groundwater monitoring and forecasting. But today we will only focus on the flood forecasting topic. So I will later share several applications that use flood early warning system. I would like to start with the application that we have in Indonesia. Later, Ministry of Public Works will also share this in more detail because we also work together with them to build this system. So in Indonesia, nowadays, we have at least 4 that I mentioned here. And there are more actually, like the landslide early warning system as well. But here we have FEWS, Jakarta Flood Early Warning System. So we developed this with Ministry of Public Work. So it's a flood early warning system for all basins crossing Jakarta city. If I remember correctly, there are 6 river basins that are passing or crossing Jakarta city. And the motor or the model that is used in this system for early warning is Sobek hydraulic model. Then we also have PSH, or Center of Excellence on Hydroinformatics. So it's a bit different than FEWS because initially this is used to store all of the data from different balai or department to this platform, and it also has a model, a hydrological model, to estimate flow discharge at any location, at any river location in Indonesia. So the model itself is also covering the whole Indonesia. We have WFlow for in Kalimantan, Java Island, Sumatra, Papua, Sulawesi. So it's already covering all, but it is still hydrological model, meaning that it's a rainfall runoff model. So you don't get any flood extent, flood depth from this platform. What you can get from this is the estimate of flow discharge on any river in Indonesia. But I think it's already quite powerful, especially in the region where we don't have any water level gauges. And it use remote sensing data set as well. So with remote sensing data and also the forecast from Meteorological Agency in Indonesia, BMKG, we make use those two to estimate the flow discharge in any river in Indonesia. Then I also know that there is a drought early warning system that we developed together with BMKG. So it's specifically for drought. And in here, in the system, we calculate drought indices using remote sensing data and ground measurement data, because the MKG, or Meteorological Agency of Indonesia, has a lot of gauges, rainfall gauges, to produce drought indices. In this platform, we don't use any model. We only do simple calculation with certain formula to calculate the drought indices, like SPI, like what else? days without rain, a simple parameter that can already use to detect whether drought might come or not. Then we also last have IWRM instrument Indonesia. Compared to the three above, JFEWS, PSH, and DEWS, this IWRM is actually a standalone application. And sorry, the DEWS actually also a standalone application, but back then the Meteorological Agency run the application every 10 days because they need to make a bulletin for days without rain every 10 days, every decadal. For IWRM, why we have this? It's because we think that apart from operational system that runs automatically, we also want to have a quick tool that allow us to do hydrological assessment, quick hydrological assessment for any region in Indonesia. And inside this, there is already a WFlow model, a hydrological model that also can be clipped. Let's say you only want to focus on certain region, you can clip and do calibration, do updates to the model using IWRM. And you can visualize all the result of the model in this platform. Another reason why we have this tool is because sometimes the model that we use, like in this case, WFlow, doesn't have an interface. Sometimes it's only like a file for input in certain format, maybe CSV file, and the output is CSV file. Of course, you can open it using Microsoft Excel, but then think about if the input and output is in raster file or in gridded file. It's not that easy to open everything in your maybe QGIS application, like graphical information system application, and dragging one by one. So with IWRM, the input can be open in FEWS, the output can be also shown in FEWS, and can be very useful for models that doesn't have any interface. And today, I will also share mainly some applications outside Indonesia that use DelFews as their core system, but mainly for flood forecasting. So the first one is from the Netherlands. It's quite famous, but of course also I still, maybe it's myself, but I find it a bit difficult still to find some the system itself, even internally. Like I want to see the system, but it's fine. It's somehow quite difficult, like because this system is installed in the Ministry of Public Works and Infrastructure in the Netherlands. So it's not in our system, not in our company server, but we help them to develop this system. So it's called RWSOS, National System for the Management and Early Warning of All Water Systems. It's a really big system. Then I will also talk about another system from Australia that we help to develop. This one is not yet operational, but we help them that to build this and make it as a proof of concept that this system can be used for operational context. So a national flood early warning system for Australia. And then I will also talk another system from UK, which is also very, very big, very nice to share, because I think this is also one of the biggest client for Deltares. And they, like the country itself, the UK is using FEWS for their forecasting system. And then we also have developed two flood early warning system with global scale that I think can be useful as well for us if there is any chance or any needs to get, let's say, river flow in any particular area in anywhere around the world, and also the water level, seawater level near the coast anywhere in the world. So there are two applications. GLOFIS stands for Global Flood Forecasting and Information System, which is operational in our Deltares server, and GLOSIS, Global Storm Surge Information System. To begin with, I will share a little bit how the Netherlands use the FEWS for operational system. So the RWSOS is a national system for the management and early warning of all water system, with focus areas on fluvial flood forecasting, coastal flood forecasting, forecasting of estuarine process, like the water quality process as well, the intrusion of salt water, management of the big lakes in the Netherlands, management of the low-lying areas, and also drought forecasting. So it's really a combination of several use systems for different purposes, and also using different various models. And this data is also shared to like the balai of the Netherlands that we call regional authorities, water boards. So all the picture that you see are some of the screen capture of the systems that they develop for hydrology, for the estuary area, for flooding, for level control. Like in this level control, they don't use the regular display, but they make a schematization. They make their own schematization so that the operator much easy. They are easier to understand. They are easier to understand the status of the water level in their region. The flood forecasting itself in the Netherlands is the responsibility of the Ministry of Public Works and organized in one central water control room. So they have a room where all the systems are shown and used in operational basis. In terms of the structures, they also also include many structures like gates, big gates. I think the biggest robot in the world at the moment, like this gate, Maslan Kering. We also have levees that is also included in the model. We also have sand dunes in the north, in the coast area, that is also fluctuating, like changing over time because of the waves from the sea, from the North Sea. So they take into account the river, the flow discharge, and also take into account the water level from the coast. So both. And they also do forecasting for the coast. So maybe since the beginning, I think I already mentioned that we need a model, but a model also need a boundary condition. A boundary condition is like the condition at the upstream. Normally it's in the upstream and downstream area. In the upstream, we normally use water level or discharge, mainly discharge, flow discharge. And in the downstream, normally it's a water level from the sea. For an upstream boundary condition, maybe it's not, it's quite common these days. Maybe you have river gauges, and maybe you also have a model to calculate it. But let's say in Indonesia, for water level, seawater level that is used for boundary condition, we normally have measurement from tide gauges. And if we want to do forecasting, we also need to have the forecast of tide gauges, right? Otherwise, this from the red line to the right, you will have nothing, and the model will say that, oh, I don't have any data, I cannot run the model. And even if you have some dummy data, like fake data, it might not be accurate. So we also need a forecast for seawater level, and it's normally generated by a model as well. Also, the input is the tide gauges, tide data, storm gauges, and the upstream is flow discharge. And we use that to predict the flood in the inland area or in the dry area. In the Netherlands itself, so they already use it. But of course, in the Netherlands, the basin that is crossing the Netherlands is also a transboundary basin, which means that the basin itself is passing several countries before ending or flowing to the Netherlands. So the success key for them, so that they can produce a good flood early warning, is to exchange information with other countries and work together. So they also share some data to the upstream neighbor countries, including the tide forecast. This is what they did for the River Rhine. So here River Rhine passing Germany, France as well, and Switzerland. And they do forecasts with lead time of 4 days. So they want to see how the flow fluctuates for the next 4 days. And if you can see here on the left, you see a lot of variabilities or uncertainties to the future. The further you go from present time, the further it fluctuates. Yeah, of course, we cannot really predict in too far sometimes. And of course, it's also because of the model input that we use. So their goal is to to have a flood forecasting with a lead time of 4 days, so that they can react if there is potential flooding in certain areas. And here the plot that you see is actually we call it a probabilistic forecasting. So we don't use only one weather forecast and also tide forecast, storm surge forecast, water level forecast, but we also use several models, several forecasts in order to generate this plot. It is getting more and more common to use this, but of course, it also depends on the, let's say, the budget and also the capacity of an institution, because running this also requires a good computer, I would say, a very good hardware. For a small basin, yes, you can do a quick run, but if you do this for a nationwide, then it's gonna take some time to finish the running. That's also one reason why these days the flood early warning system is also put into the cloud, so that all the processing is done in the cloud with their big capacity and memory, and we can also scale up the infrastructure. We can run a small one, but once we want to do a big analysis or more complex analysis, then we can ask the cloud provider to open or give more RAM or memory to do this processing. Instead of if we buy our own server with specific specification, then you need to buy and maintain and make sure everything works. Whereas in the cloud, and they guarantee that they will do the backup, they will also make sure it's running all the time. So there is also a good reason why we also want to encourage client to put into the cloud. But it depends. Sometimes, it also depends on the country or our client. If they want to put into the cloud, then that's fine. But sometimes also for security reason, maybe they don't want to. But in terms of benefit, I think using cloud is much more nice to in the future. So this is the display of the flood forecasting for the North Sea. So they have a model, sea model here using a Delft 3D FM, a hydrodynamic model. And they also have several stations from UK and also the Netherlands as an input for their model in order to generate the forecast, which is used to which is used for do the flood simulation for the inland part of the Netherlands. So this is already one model and one platform. And then they also plot those data like this, like in the right top figure. So they not only display the the measurement, the near real time data, but they also compare it with the historical statistic. So they in the projector you cannot see it clearly, but in the slides you can see that the gray area is like the minimum and maximum, the percentile that is also can be useful to tell that you are at the moment experiencing drought or flood situation. And of course, ensemble forecasts getting more and more popular these days. From this ensemble, you need huge computation, but also from this you can generate the median, like in order to at least see the trend of all the weather prediction. You just take the median, and that's already good enough to guide the forecaster that this is the probability of flooding or decreasing river discharge. And of course, they also build, they like to build a nice infographics or dashboard semantic display, as you can see in here. So all the red arrows and green arrows can is linked to the graph and tables, but at the same time, the values can also be changed over time. If you hover the mouse and move this time slider, you can also see the values changing over time, which I think it's nice to have for any application. Then in terms of bulletin, this is what they have. So the bulletin itself, they have, or like the output, the final output differs from the perspective of users. So for daily forecasters, this is what they produce, which is in the application itself. Only a graph with some area where the forecast might lead to, or what the flow discharge might lead to. But then they also translate these forecasts into a bulletin like in the middle. So they have a table, yes, with the values, the water level values, the threshold, and also when in the flow might goes down, and a more detailed information about the condition of certain location, which is used for regional coordination. So the one who really need to take action in the field. Not only that, they also produce a website that can be accessed to their citizen and to the public. And yeah, it's much more simpler, just showing the water level and also the color, basically. I think these days they also have more and more information, but at least with this, the citizen can see whether there is a risk or potential risk in their area. So again, warnings need to be disseminated, but we also need to think who are getting the warning and how are we going to deliver the message to the end user. Is it for daily forecaster? Is it for the one who will take action, regional coordinators, or for national coordination, and also just for the prime minister or the ministry to understand the situation where the flood occurs? So this is what they did, and also shows the level of detail of the output. Then I'll move on to the second case in Australia, this is also quite a nice example. Like we know already, right, that Australia is a very big continent. It's very massive, and they want to have a flood forecasting for their entire country, which is very big. And also, if you think about the modeling, the model, you need to have a very big model. And if you also want to have a good quality of a model, then maybe the model needs like the cell or the grid of the cell needs to be very fine, very small, like maybe one or not 1 meter, but maybe 10 meter by 10 meter for the entire country, which is, yeah, I can imagine running this in your computer might take, I don't know, some days. But they still want to have it, so they request for a flood intelligence service, FEWS, and they want this service to allow Australian government to make informed decision before, during, and after flood events on a national scale. By before and during events is like they want to know where the inundation area is likely to happen, and to assist tactical decision making to protect lives and property. So that's a common, that's a really early warning. But after the events as well, which store or keep the model simulation, so accurate inundation footprints to inform relief, short-term and long-term recovery activities. So after the events, they need to have a flat footprint that allows them to react, which area that they can put their their tent in the area. And the solution needs to be shareable as well across government, linked to official forecasts like the weather forecast or warning wherever possible, and provide an open approach to the modeling, meaning they can choose which model that they want, like flexible to use any model. So we come in and we propose this solution where the open to mix of existing and new is in this right part. So the modeling framework, they have several models. ORBS, WFlow is from us, a hydrological model. Sphinx is also from us, hydrodynamic model. WaterRide is from them, hydro inundation model, hydraulic model. So at least this part can already be connected to FEWS, which is good. So we already cover the open part. Then we need to link this to existing forecasts, existing bureau products. So we can link that with or get that data and put it into FEWS using the import module. Then we also have the shared option via FEWS API that I mentioned that can be used, can be used for building a website and a mobile app, connecting to other system, and also have open archive that also do similar to API, but only for archiving purposes, and national scale possible. So although this is still proof of concept, but we can build it in days, basically. with all the models ready. In terms of multimodal open approach, one of the reasons why they want to have it is because they want to provide best forecasts in any location. So they already have several models in Australia, and they know that this model fits for that purpose. And let's say for high population areas, so it's in the city, they have already a detailed flood studies there, where they use water right model to combine existing flood maps with official warning to provide detailed and accurate forecasts. So they use that. But for urban and regional areas, so for other areas where population are there and infrastructure, and we also have the digital elevation model, they want to use Sphinx and WFlow because Sphinx provides inundation forecast, and it's the branding in Delta Res for Sphinx is that this is a hydraulic model, but much faster than Sobek and the predecessor of Sobek. So, but this is also a raster file, a raster model, a gridded model. So it can give you the area where the flood might occur. So Sphinx was used to provide inundation forecast, especially, and it can also be used for national scale. So there are many blocks of Sphinx surrounding us in the surrounding Australia that we built, and we use that to give a flood forecast in Australia. That's for the downstream boundary part. But as for upstream boundary part, we still need to have flow discharge, right? So if we yeah, of course, I think Australia has a good database as well in terms of flow discharge. But in national scale, and we also still do it for prototype, proof of concept, it is going to take more time to collect those data from different bureau in the country. So instead, we build a model, a hydrological model that covers Australia, and we take that output of that model, the flow discharge in the upstream area, and use it as an input for the Sphinx model. So we combine two model here, Sphinx and WFlow. They also actually want to focus on some regional areas, but mostly on the rural part, where no quality DEM data, not a lot of infrastructure, but in this work, it's not part of the work. So this part we didn't really do it, and we only focus on the high population urban area using water right, and urban regional areas using Sphinx and WFlow. So in one system, we have 3 models, which is also show the capabilities of FEWS handling with many models. So this is the WFlow hydrology model on the left, and it's already calibrated with the observation for an event in Brisbane in 2011. The simulation and calibration looks good, and from those WFlow, we use that input to run hydraulic model using Sphinx. So the same, it's in Brisbane 2011. So the simulated is in orange or in red, and the observed is in blue. It looks similar. At least can show that FEWS and the model gives a good correlation with the observation. So back then they said that, yeah, this can be done and can also be used for national flood forecasting for Australia. And if you check the water depth in the blue star here, it looks the same, very close. At least they can take the peak water depth, and also the in the downstream where the tidal influence as well has influence. It also gives a good estimate. So the output of the, when we talk about the output of the platform, they produce maximum water level. So this is their goal. In the beginning, I mentioned that we first need to think about the goal. So their goal was to find the maximum water level, which is produced by the Sphinx model, the maximum depth, and also for archiving and also for post-processing after the event. They want to have it in an easy file that can be used for many further analysis, which is in shape file. It's a format to store factor data. So these three are the main output of their FEWS, Australia Flood Early Warning System intelligence system. Then the third example, it's coming from the UK now. It is called Flood Forecasting Incident Management Forecasting System. And it's developed together with Deltares and Environment Agency. So now Environment Agency is the one who maintains it. They use FEWS a lot since the beginning of FEWS development. And the flood forecasting service is a partnership between meteorologists and hydrologists. On the top right, you can see how dense their rain gauges are. They are very close to another. It's incredible how they have these rain gauges. And normally, if you see something like this, it's in the context of operational system, it is all telemetry system. So the stations are already sending the data to the database and not manually written anymore by staff or men. It's really incredible, like in developed countries, that they have this many gauges. They also make use of remote sensing and also weather forecast ensemble. So here on the left side is the ensemble, the display of the forecast ensemble. They also use the ocean model for their downstream boundary. And then, yeah, the display looks the same with other application, but they also provide a nice warning to the client where it not only give an area, a color, water level, a depth, a flood depth, but also the description about the potential hazard itself. Later, I will show you in more detail. So that system, the IMFS, actually is the successor of this FEWS and FFS, National Flood Forecasting System in England and Wales, which was implemented in 2003 and until 2006. And harmonization of 8 regions with 8 different systems and procedures. So back then they also have different systems, they have different procedures to maintain maintain and produce the warning, and even have many models inside, 20 different model types, NAM, Mike 11, etc. And it's already covering 2,000 forecasting location or points, which is a lot. So in England, they use also not only fluvial, which is in fluvial is in the river, flooding coming from the river, but also coastal forecasting in order to operate their barriers here. Because if there is a storm and the seawater level raise too high, it can also makes a flood in the inland part of UK. What I think and also want to share, maybe it's not very common. Actually, in Indonesia, we also try to implement this, but yeah, at least in this system, in this IMFS system, it is still operational. Is that the interesting part is that they are using public data as well for their warning and understanding their their system status. So they have I don't know how to call it, but it's a tool to take a tweet from, nowadays it's a X, from a Twitter. If there is a if citizen say that, oh, this is a warning with there is a flood in this area with how many meters, there is an API or like a connector that can be used to put those information into flood early warning system. So when we think about flood early warning system, normally we only think about the data from gauges, from radar, from model, from satellite imagery. But this time, apparently, they try to also better understand the system by integrating data that is already there for a while, which is from the Twitter, from someone posting, and then through data analytics, and they take those information and say, okay, in certain area there is a flooding, and put it into the FEWS display. And also this is very useful because you can also validate your model whether the flood really occurs or not in those regions. So not only the model and also observation, there is a feedback from the public as well, and then can be used to check whether the flood forecast is correct or not before we approve the forecast and display it in a website. In more advanced application like this, they have a modifiers as well. So normally we think, okay, maybe for flood early warning system that I have, I will only have a rainfall model run and get the output, as simple as that. But in reality, we have many structures many water structures, dike, gate, pump, etc. So and they also have different operating rules. In normal condition, maybe we can choose one of them. But in emergency situation, we might need to, let's say, use all the pumps that we have in their maximum capacity. So modifiers here in DelFuse is used to, actually to choose which option is the most efficient solution to reduce the flood. Do we need to run all the pumps, or do we just need run the pump, two pumps with full capacity? So with modifiers, we can try to run the model with different scenarios. And from that, we know, okay, maybe from this simulation, turns out that with this forecast, we will be still protected from flooding if we only run two pumps with full capacity instead of using all the pumps that we have. So this is what they did in the UK. They have modifiers. They even can modify the rainfall. So maybe from the OP is operational system. BE is best estimate, and RWC is the run with correction. So they can even manipulate the rainfall in case the typhoon or the storm moves a little bit to the north or to the south. So they can do simulation by using modifiers, because we cannot, maybe sometimes we cannot trust the forecast for sure. And that's why we update the forecast every 4 hours, every 6 hours, to check again whether the previous forecast and this forecast looks the same, or the intensity or the potential hazard is getting higher or not. So they already implement modifiers, which is the advanced one for flood early warning system. And this is the output of IMFS. I think it's very different from the display that we saw earlier, because you don't see any this FEWS display, the special display, because this is actually from their website. So it's their website, but in the back end, they use flood early warning system and make use of the API to build this website. I really encourage you to check this website, because it's really a nice website. So when you open the link, you can also see first which area are under warning and alert, flood alert. And then if you zoom again, zoom to certain zoom level, you can see the flood area, no longer the flood warning icon. And if you click in that area, you also get some description about the potential hazard that might happen in those areas. And this also that's using DelFuse API. Of course, you need more people, like IT people, to develop the website, but this is doable. Then I will talk about two more systems. This one is pretty quick. So GLOFIS. So we have a global flood forecasting system and information system covering the entire world. So we use a hydrological model, multiple weather forecasting products, including Ensemble. So we also have Ensemble forecasts to force multiple hydrological models, such as PCR Globe WB, W3RA, and WFlow models that we have. They also it also run twice a day to produce 10 days probabilistic water level and discharge forecast. And it's already covering the whole world. It's running operational in our internal server. And it's also used for an application, a client in Serbia, where we take the upstream boundary condition from this GloFish system. So we share some data through API, through GloFish FEWS API, so that they get water level data on the upstream part, and then they can do the flood modeling further using those input. More advanced technique like data assimilation is also applied here. For selected basins where observations are available in near real time. I think mostly still in the Europe, they implement this data assimilation. But still, this can also be useful for regions where they don't have any flood early warning system, they don't have any data to begin with, and they want to at least see how the data in their region and try to understand the process of providing flood early warning system. Because investing directly, building a flood early warning system might be costly. But if you want to try it first, then you can just ask some part of the region and get the access to this. So that for water level and discharge. At the same time, we also have a GLOSIS, Global Tide and Storm Surge model, covering the entire world. It's using GTSM, a Global Tide and Storm Surge model, still the same Delta Res software, Delta 3D FM software, and producing a forecast for the next 7 to 10 days. And the forecast itself is produced every 6 hours. This also means that the running time for the model is very fast. Like within 6 hours, the model needs to run again. So the simulation needs to be finished before 6 hours. When you think of a global scale, I think this is amazing. Like the computation power is gonna be very, very, very big. And it's luckily this one is already available in the website, although not the forecast yet. The historical one, later I will show that this is already available and can be used, although you need still some adjustment. But I think the quality is already quite okay if you don't have any data at all. So this is some of the simulation, and the green dots here are the locations where you can retrieve the water level in any part of the coast. And you can see how dense it is in the Europe region, because they first developed that for Europe. But now I want to share with you, oh, sorry, not yet. So it is used for many applications here. So they use it in our lab. So we have a dedicated room to show that GLOSIS, that application, where client can come and see what we can provide. We also have provide those information to several systems, like here, MSG real-time, and then near real-time hindcast provisioning to Sea Drift Reinsurance platform. And then we also provide that through API to Blue Earth data, and also to FEWS INA Mozambique. So again, maybe talking back about the option 2 that I share with Mr. Boy, that we can just retrieve the data or get the data output from another platform to our platform, which is also possible. Still few system, but we only take the output. So this is an example of the quality of GTSM model from GloFish in Malaysia. So I have a project in Malaysia at the moment, and I try to compare the observation and also the model by shifting the time data with because of the time difference +7 for this June 2019. It looks promising, and also I also displayed for all the months in a year. Looks okay, but again, I want to stress the importance of observation data, because when I check on year 2018, I see that there is a mismatch. At the moment, we are still not sure which one is correct, but only this year, somehow the measurement gives a, not match, gives a quite a shift, and also, something to be checked again to the client, whether there is a different gauge or a new instrument installed or maintenance whatsoever. But this is why observed data is also still important, even though you now have a lot of options from remote sensing, from the model, from many sources that you can get. So to summarize, in topic 3, we know already that DelFews is used extensively for flood forecasting and flood early warning, not only in Indonesia, but also around the world. It is flexible because it offers various output, allowing user to tailor their visualization, their needs, and scalable as well. You can start from little up to global scale, like GloFish and GloSys, and then interconnectable as well. So like some example that use GloFish and GloSys for their flood early warning system. So that's the summary of topic 3. And before we move to the discussion or question and answer session, I want to share a bit because I think the moment is very good. So so we have a community. The way we learn is also through sharing and also listening to other DelFews users around the world. So we have a website where all the users, DelFews users, can share their experience and learn from each other. DelFews community website, DelFews portal, where we can also discuss our problem there if you need it, and then also DelFews documentation. And every year we have this kind of event. For this year, somewhere in November, and in the next slide I will share, but it's really a nice opportunity to be there and get to know with other DelFews users around the world, because many users are this day using DelFews because it's free of charge and the capability to connect with many models. So in that Delta REST software days, we also have several courses, which are free and also not. Some are hybrid. but I really encourage to join the free one, which is also some of them are online, which is free. You can learn the most recent updates of Delphius and also how Delphius is used in other region, like in Delphius user days 1 and 2. These two are talking about how they use Delphius in their country. So with that, I would conclude my presentation. And thank you all for your participation and attention. And if there is still any question, I would be happy to answer. Thank you.
Is there anyone who would like to ask or discuss with Mr. Christian? For further question, all participants could contact your email, maybe, sir.
Yeah. That would be also fine. Thank you.
Thank you very much, Mr. Christian Alfonso Liguri, for sharing your valuable insight of the introduction and implementation Delphius for FEWS for us on behalf Center for Water Research and Settlement Competency Development. We would like to say thank you. Thank you very much, sir. Still Christian until Friday. So now take a break for almost 1 p.m. Western Indonesian time zone. Thank you.